Hello students, welcome to the Thrust of Curiosity. Today we are going to study Liouville's theorem. This is very important theorem in statistical mechanics. Here we consider volume omega in a phase space with total surface area S. This means this phase space, this volume is enclosed area. Now this area vector at some point is making this normal n cap. So the total flux or the total number of phase points coming out of this first portion can be written as rho, which is density of phase space, or we can call it as a distribution function, into this q dot bar. Bar is velocity, so it's a vector, so that's why it's bar, and it's a dot product with the area, because you can see here this is the velocity because the particles can move in this direction, but there is a normal area is in the different direction. So there can be possibility of some different angle, and therefore this is included in this. Or we can further simplify this and we can separate this area. So this is the magnitude of the area, and this is the unit vector in this direction. Now, so because this is the flux coming out, or the total number of phase points coming out of the area ds, the total area, the total phase points coming out of this volume will be equal to closed integration, this is surface integration over ds, and this is remaining same. So this is for this much ds area, and this complete is this case. If we use Gauss-Liouville's theorem, we can convert this closed surface integral into the volume integral. So omega is the volume of this phase space. So this is the vector. So of this vector, we are getting the divergence. So this is the using Gauss-Liouville's theorem. Now, if there is a number of phase points are coming out of this phase volume, then with time the phase volume or the phase density will decrease. So this decrement in the phase volume is denoted by delta rho by delta t, and over the entire volume there will be some decrement in the phase density, and therefore there is a negative sign. So the total flux coming out of the volume must be equal to the total change in the phase density. And by rearranging this, we will get this equation, and this is the equation of continuity. This tells us that the phase density of the phase space remains conserved. That is, if there is some change, positive change, there will be some negative change in some other area or in some other volume region. Now, as we know, this density or distribution function is the function of q and p. Therefore, we can expand this divergence in derivative with respect to q and derivative with respect to p. So, if we further expand this, you can see this is the u into v rule. So, this is also function, this is also function. So, we will take derivative of this, then this is constant, and if we are taking the derivative of second term, then the first term is constant. So from this part, we are getting, first we will keep q dot constant, and therefore gamma rho by gamma qi. From second term, we will get pi dot constant and gamma rho by gamma pi. So we will get this two terms. We will get two more terms in which rho is constant. So we are taking this rho. We are taking this rho constant outside, and remaining terms are gamma qi dot by gamma qi and gamma pi dot by gamma. Now, because in phase space we consider that q and qi dot are independent of each other, therefore this term becomes 0. Similarly, this term also becomes 0. Therefore, the second term in this equation will be vanished. Now, using Hamilton's chemical equations, we have q dot is equal to gamma h by gamma q, and pi dot is equal to minus gamma h by gamma qi. Okay, here also I will write qi and pi. where h is the Hamiltonian of that system, Hamiltonian of the system. Now we will use this and put in this equation. So divergence of rho q I dot is equal to summation over, instead of q I dot we are writing dash by dot pi, and instead of pi dot we are writing minus dash by dot q I from these two equations. And now you can see this p and q have exchanged here with the minus sign. So this is nothing but the Poisson's bracket. So the Poisson bracket we will write this first one is Hamiltonian, and then second term is distribution function of the phase density. So if you put this in this equation, we will get this Poisson bracket plus lambda rho by lambda t is equal to 0. And further, this is nothing but the total change in the distribution function over the time. So this is total derivative, and this is called as a Liouville's theorem. So this theorem suggests that over the time, the distribution density or distribution function is constant over the time for such cases. And if the flow is steady, then the partial derivative will also become 0. In that case, the Poisson bracket of h and rho is equal to 0. This means this rho, which is earlier we considered this is function of q and p, that is also constant function. So this will form a constant surface. So if you are traveling on the phase space, for that particular phase space, this rho is not going to change even if we are changing q and p. So this is for the phase space which is stationary. So such phase space or such phase volume we will call as a stationary phase space.